Welcome to section 20.2, part 2. This is the 204th session of the CISSP exam prep series. This part turns to the security threats and controls that live inside databases themselves. In this session, we'll examine how databases defend the data they hold. We'll answer several questions. How do you secure a database holding many classification levels? How does concurrency protect data during simultaneous edits? What are aggregation and inference attacks? What granular controls tighten access? How do you defend against those clever deductions? And what do connectivity layers and non-relational databases change? Why does this matter beyond the exam? Because attacks on databases rarely look like break-ins. They often look like ordinary, authorized queries that quietly add up to something forbidden. Imagine a government payroll system where a clerk can see totals, but not individual salaries. The real danger is not a stolen password. It is the clerk deducing one person's pay from a series of legitimate lookups. Knowing these subtle threats lets you close doors an attacker would otherwise walk through in plain sight. How do you secure a database holding many classification levels? A multi-level security database stores information at several classification levels and must check each user's clearance before returning only what they are cleared to see. The central danger is database contamination, where data of different classifications or need-to-know requirements gets mixed together improperly. To add multi-level protection to a legacy or weak database, administrators often place a trusted front end between users and the system. Another elegant tool is the database view, a stored query that presents data as if it were its own table, letting you collate, aggregate, or restrict what each user sees without handing over the raw tables. Think of a view as a stencil laid over a document, exposing only the words a given reader is allowed to see. How does concurrency protect data during simultaneous edits? Concurrency, also called edit control, is a preventive mechanism that keeps stored data correct when multiple processes touch it at once. Without it, two problems appear. A lost update happens when two processes update the database unaware of each other, so a warehouse count that should rise by 2 rises by only 1. A dirty read happens when one process reads a record from a transaction that never successfully committed, leaving it working with half-written data. Concurrency solves this with a lock that lets one user change data while blocking others, then an unlock that restores access once the change is done. Paired with auditing, it can even become a detection control by tracking changes. Think of it as one editor checking out a shared document so no one else can overwrite their work mid-edit. What is an aggregation attack? The query language offers functions that combine records to produce summary information, a process called aggregation, and it carries a hidden risk. An aggregation attack gathers many low-value or low-sensitivity facts and combines them into something of higher value or sensitivity. Consider a records clerk authorized to update where individual soldiers are stationed. Each single transfer seems harmless, but with access to aggregate functions, the clerk could count the troops at every base worldwide, force levels that are closely guarded secrets. So control access to aggregate functions tightly and weigh what they might reveal. Combining defense in depth, need to know, and least privilege blunts these attacks. Think of it as individual puzzle pieces that mean nothing alone but reveal a sensitive picture once assembled. What is an inference attack? Inference resembles aggregation, but relies on human deduction rather than raw computing power, combining non-sensitive pieces to conclude something classified. Picture an accounting clerk allowed to see total salary figures for any past date, and also the hiring dates of employees, but never individual salaries. If exactly one person was hired on a certain date, the clerk can compare the salary total from that day against the day before and deduce that person's exact pay. The defenses are constant vigilance over permissions, deliberately blurring data, such as rounding salaries to the nearest large amount and partitioning the database. Think of it as reading between the lines, where two innocent facts placed side by side quietly reveal a third that was meant to stay hidden. What granular controls tighten database access? Databases offer several fine-grained mechanisms. Semantic integrity ensures user actions never break structural rules, keeping data within valid ranges and honoring uniqueness constraints. Time and date stamps preserve integrity in distributed systems, applying replicated changes in correct chronological order across every copy. Content-dependent access control decides access based on the actual contents of the object being reached, which is precise but adds processing overhead. Cell suppression hides individual fields or cells or wraps extra restrictions around them. And context-dependent access control looks at the bigger picture, judging how each element relates to the overall activity, since a single element that looks innocent alone may prove telling in context. Think of these as adjustable lenses, each narrowing exactly what a user can bring into focus. How do you defend against aggregation and inference more structurally? Beyond watching permissions, several architectural defenses help. Database partitioning splits one database into multiple parts, each with its own distinct security level or content type, so no single view exposes too much. Polyinstantiation lets two rows share the same apparent primary key while holding different data for different clearance levels. Imagine a ship whose true, classified location is stored for cleared users, while a decoy record shows a routine patrol to everyone else, so a lower cleared user never notices anything was hidden. It costs extra storage but foils inference. Finally, noise and perturbation inserts false or misleading data to thwart confidentiality attacks, though you must apply it carefully so it never corrupts real operations. Think of these as compartments, decoys, and smoke, each designed to keep an observer from assembling the true picture. What does a connectivity layer like Open Database Connectivity change? Open Database Connectivity lets applications talk to many different kinds of databases without being programmed specifically for each one. It sits as a proxy between the application and the back-end database drivers, freeing developers to build solutions without worrying about which database engine sits behind them. Think of it as a universal travel adapter, letting one plug work in outlets of every shape without rewiring the appliance. What do non-relational databases change? As data grows and stops fitting neatly into tables, many organizations turn to non-relational databases, which use models other than the relational one. Three common types matter. A key-value store is the simplest, pairing a unique key with a data value, ideal for high-speed and very large datasets. A graph database stores data as nodes and the edges that connect them, perfect for networks like social connections or geography. A document store keeps richer, structured documents indexed by keys, often in common data interchange formats. Because their security models can differ sharply from relational databases, learn the security features of whatever you use and design controls with your database team. Think of these as specialized filing systems, each shaped for a kind of data the classic table struggles to hold. So let's bring it together. Multi-level databases guard mixed classifications with trusted front ends and views, while concurrency locks data against lost updates and dirty reads. Aggregation and inference attacks assemble harmless facts into forbidden ones, countered by tight permissions, granular controls, partitioning, polyinstantiation, and noise. Connectivity layers let applications reach any database, and non-relational databases trade tables for key value, graph, and document models with their own security needs. Master these, and you can protect data even when every individual query looks perfectly legitimate. The MCQs covering all the topics and concepts from this session are available on rootcloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.